Hi, this is Greg, and this is my materials engineering in 5 minutes. It's actually a bit over 7 minutes, but there you go. We've seen that with materials we can divide them up into three big groups: metals, ceramics and polymers, and we can do that because all the metals have similar properties, all the ceramics have similar properties, and all the polymers have similar properties. For example, metals can be strong, they're usually ductile, they can be soft or hard, but they're good conductors of electricity and heat. Polymers are soft and weak, are floppy, and by that I mean they're not very stiff, and they're non-conductors. And of course our ceramics tend to be hard and brittle and are non-conductors. It's important to appreciate there's a wide variation within each of these groups. So we have weaker, softer metals, we have harder, stronger metals, and so on. But I guess the important thing is, what do we know about material science and engineering? Well, there's a basic rule, and that basic rule is one that says processing controls the structure, which controls the properties. You had a look at some processing, and you had a look at casting, sintering, cold working, extrusion, rolling, drawing, forging, and some of these can be done on metals, ceramics and polymers, not just particularly one group. We also had structures, and the structures we're talking about are such things as bonding, crystal structure, imperfections, grain boundaries. We've seen that metals are metallically bonded and therefore they conduct electricity, for example. We've seen that face-centered cubic metals tend to be more ductile than hexagonal close packed, and so on. We've seen the effect of imperfections, grains and grain boundaries, and so on. And the properties we looked at, mainly mechanical, strength, hardness, ductility comes in there, but we also looked at conductivity, and we also looked at some chemical properties such as degradation and corrosion. But what about these structures? How do they control the properties? Well, let's look at metals to start with. Really here we're talking about dislocations. Dislocations give us ductility in a metal. So if we increase the obstacles, if we make it harder for dislocations to move, we make the metal harder and stronger. Of course, as I've said during the semester, that if we increase strength and hardness, we stop dislocation movement, then we reduce ductility, because it's the dislocations that give us the ductility. So what obstacles can there be? Well, we can have grain boundaries, and that gives rise to grain size hardening. The smaller the grains, the more grain boundaries there are for the dislocations to meet, and we find that dislocations find it very difficult to get past grain boundaries. We can introduce lattice distortion into the crystal structure, and that can be done by alloying, adding other metals, so we have atoms of different size, creating distortion in the lattice, substitutional, interstitials, so on. Or we can have precipitation hardening, where we finally disperse a second phase through the first phase, and that second phase gives us distortion in the lattice as well. Or it could be simply other dislocations through cold work. We get this thing called work hardening, where we multiply the number of dislocations and they get tangled up. And we also get dislocation pile up on grain boundaries and that sort of thing. Of course, we can also decrease the obstacles and we get softening. So for example, for grain size hardening, if we heat the metal back up and allow the grains to grow, we can reduce the hardness and increase the ductility. For alloying, there's really no softening mechanism, but for precipitation hardening, we can heat it back up into the single phase region and dissolve all those precipitates and start again. And for work hardening, we can do recrystallization and grain growth. Remember the aluminium bar in the lab you did in the last couple of weeks. Of course, with alloying and precipitation hardening, we use phase diagrams. We looked at phases, we looked at lever rules, or more precisely the inverse lever rule, We also looked at microconstituents. It's very important not to confuse microconstituents with phases. The phase diagrams give us an idea what happens under equilibrium cooling, but we also looked at non-equilibrium cooling, and in particular we looked at steels, we looked at TTT diagrams, and we saw that the faster we cool the steel, the harder and more brittle it gets, and that's because we're increasing the distortion in the lattice, so we're hindering dislocation movement. Also, age hardening really is a non-equilibrium cooling where we quench the steel from the single phase region. So there's a couple of examples of non-equilibrium cooling that we looked at. For polymers, it's the same sort of concept. What we've got to work out is what gives rise to the changing of shape when we apply a load to a polymer. Well, it's not dislocations in this case. What it is the movement of chains past one another. So if we hinder chain movement or interchain movement, we get the same effect as we're hindering dislocations. So if we have these polymer chains that have weak secondary bonds between them, if we make it harder for them to slide past one another, then we will get a harder, stronger polymer. We looked at thermoplastics. Remember the definition of that. You can soften with heat. Thermosets, which we can't. The thermosets are a good example. We have primary bonds, strong covalent bonds between the chains that makes them very hard, and you can't move the chains past one another, so we have a hard, brittle material. For the thermoplastics, we have an amorphous. We can have amorphous or crystalline thermoplastics. The amorphous comes about because we hang large side groups off the chains, and these interfere with the movement of chains past one another. So we go from something like polyethylene, which has no large side groups, and the chains can move past one another fairly easily. We go to something like perspex that has large side groups, and it becomes very difficult to move chains past one another, and we end up with a brittle polymer. We also looked at the effect of TG for the thermoplastics. And remember what TG is, and relate that back to the structure. For example, check out polyethylene and perspex. Why is the TG of perspex much higher? We also looked at degradation and corrosion. That's chemical properties, as I mentioned before. But for ceramics, we also see that the microstructure, or the structure, controls the properties, and not surprising. But in this case, we find that because of the ionic covalent bonds in the ceramic, we don't get dislocation movement, or very limited dislocation movement, which is why they're brittle. But we find that it's the largest microstructural feature which will control strength. So that could be a large pore, or a large grain, or even a crack, some damage in the surface. That will control the strength. And we can use the fracture mechanics equation that we used at the beginning of semester. We can look at that and replace A, the crack length, with A, the largest microstructural feature. So that's it. It sort of sums it all up there. For corrosion, you should look at the two equations for anode and cathode, and you should be able to describe such things as crevice corrosion or galvanic corrosion, those sorts of corrosions, using those equations. What I'd like to say is that you should go back and have a look at the labs. If you understand the corrosion lab, go through that. Understand the heat treatment lab, go through that. All those labs are there to reinforce stuff that's been given in lectures. So my suggestion to you is to use the labs as a good source of revision. If you understand the labs, you'll understand a lot of the content of the lectures. Okay, thank you very much.